Hello and welcome to part 2 of step 5. So as part 1, we did a lot of our definitions and we did proofs solving an equation. Now we're going to move into some geometric topics of proofs. So in this first one, we're going to talk about how to write a proof using segments. So we have already sort of talked about segment addition. We didn't call it that. But now we're going to learn the official name. So the segment addition postulate, if A, B, and C are collinear, okay, remember that means that they are all on the same line. If B is between A and C, then AB plus BC equals AC. So we've already kind of done this, right? Like if we knew that AB was 7 and BC was 3, let's say AC would be 10. Whether we had two of the parts and we wanted to find the total, or maybe the total in one of the parts. Okay, but we've already kind of seen that. But the formal name of that is segment addition postulate. Okay, that word postulate is just a fancy name. Another way to say theorem. If you mix up postulate versus theorem, that's okay. We really just want to make sure that you know that it's the segment addition. We're adding segments together to get a larger segment. Okay, so then this first one is our first taste of actually writing a geometric proof. Okay, so we're going to prove that CE is congruent to FE and ED is congruent to EG. Then CD is congruent to FG. So we're going to start with our given. Notice we have all the statements. We're just providing the reasons here. So we have that CE is congruent to FE and ED is congruent to EG. Remember, we always start with our given. Okay, that doesn't change. Okay, remember that little symbol there means that they're congruent. So I'm going to go ahead and mark on here that these two are congruent with one tick mark. Okay, and then if you notice from statement 1 to statement 2, we have essentially the same information. The only thing that's changed is that instead of these congruent signs, we've now switched them to equal signs. Okay, so the first statement is saying that these are congruent. The second statement is saying that they have equal lengths. Okay, which we know if they're congruent, then they do have equal lengths because we know what congruence means. So when we switch that equal sign for a congruent sign or a congruent sign for an equal sign, that's just showing that we know what the word congruent means. Sorry about that. So since we know what the word congruence means, we're going to say that this is just the definition of congruence. Okay. Excuse me. So that allows us to say that, okay, if they have the same length, we're now going to move into writing that when we add CE plus ED, we get CD, and FE plus EG equals, sorry, let's just pause with number 3. CE plus ED equals CD. When we add segments together, this is our segment addition postulate. Okay, and then you notice that 3 and 4 look very similar. Okay, the only difference is that CE and FE changed and ED and EG changed. Okay, we're able to take out CE for FE, because we know that these are equal. And we substituted ED for EG because, again, we know that these are equal. So when we replace something that is equal, this is our substitution. Okay, then continuing on, FE plus EG. So we're looking at the two smaller pieces of this segment. FE and EG together give us FG, which again, we're adding two segments together to give us a larger segment. This is our segment addition postulate. Okay, and then now we're jumping and saying, now we can say that CD equals FG, which means that we're saying that their lengths are equal. Okay, and we're able to say that because we said that CD and FG are equal to the same thing, right? These are the same segments that are equal to each other. So we used substitution again. And then we're moving from that equal sign to that congruent sign. So remember, when we switch from equal to congruent or congruent back to equal, this is our definition of congruent because we know what the word congruence means. Okay, let's do one more. We'll skip that one for now. Okay, notice in this chart our properties of segment congruence are reflexive, symmetric, and transitive. These all appear up in your chart up above in part 1. Okay, another explanation of transitive. So we're going to look at this one. So that big paragraph just explains all that our given is and what we're asked to prove. Okay, so this time our given is that x is the midpoint of sy, z is the midpoint of yf, and xy is equal to yz. So remember, we always put our given first. Okay. The one thing too is that we cannot assume that we have a midpoint or we have a segment like a bisector of any kind unless we are told that. So the next step is that Sx is congruent to xy. And we know that because in our given, it said that x is a midpoint of sy. So we're going to use the midpoint theorem here. You might also see, instead of midpoint theorem, definition of a midpoint. That's another way to say it. And either way is fine. We won't take off for either one, okay? And then it also has that YZ is congruent to ZF. We'll mark those with 2 lines so that we can show that. And then we also, what did we have? XY congruent to YZ. So that connects back to the fact that we know that XY equals YZ. Right? When we just swap out that equal sign for the congruent sign, we're going to call that definition of congruence. Okay, so then now we have a lot of things that are congruent to each other. They conveniently color-coded some stuff, right? Like we have SX is red, XY is blue, we have green, and we have purple. So notice, we know that red is congruent to blue. We know green is congruent to purple, and blue is congruent to green. So because we know that red is congruent to blue, and blue is congruent to green, we can step over the XY, right? We can kind of cross that out. And when we do that, remember that's called our transitive property. Okay, and then notice we have SX is congruent to ZF. So from 4 to 5, all we did is we swapped out YZ for ZF. We're allowed to do that because we know that they're congruent there. And if we're swapping things out, you could reason that this is transitive property, right? Because we're still just connecting things that are equal. Or if you wanted to say substitution, that would be okay too, because you're just replacing an equal or a congruent segment with a congruent segment. Okay, and then notice in the last, from 5 to 6, all we did is we allowed those two segments to switch sides, and that would be our symmetric property. Okay, and that is it for part 2.